Welcome to Math TV with Professor V. In this video, we're going to look at sections 3.1 through 3.3 for statistics, Math 10. In 3.1, we're going to talk about measures of center, 3.2 measures of variation, and then 3.3 is Chebyshev's rule and the empirical rule. So first, we're going to talk about how to describe a set of data. And one of the characteristics that we like to have information about is where the center of that data set is. And there's more than one way that we can describe where the center is. So that's what we're going to go over right now. So the first way that we measure the center of a data set is by using the mean. And this is probably the one that you're the most familiar with already. So the mean is the arithmetic average, all right, of a list of values. So what that means is to calculate the mean, you're going to add all of the values that are in your data set and then divide by the total number of values. We use the symbol x bar to represent the sample mean. Okay? And so the formula basically to find x bar is you would add up every single value in your data set, and notice we use subscripts to denote which value we're talking about. So we're going to add up x1, x2, x3, all the way up to xn, little n, and divide that by n. This n, that represents the number of values that are in the sample. That's the sample size. Okay? And if you're familiar with sigma notation, in math, we have a way to abbreviate writing x1 all the way up to xn. We can write it's the sum of all of our x's. If we're going to get picky, I would say x sub I equals 1 to n, and then we divide all of that by n. Okay? You might see it just written as the sum of x over n, and that's fine too. Okay, good. And you've probably heard of averaging things before. You've probably done it yourself, so it shouldn't be too new of an idea. This is what we refer to as the mean of a data set. So now let's look at an example. Excuse me. Forbes magazine prints an annual top earning non-living celebrities list based on royalties and estate earnings. Figures represent millions of dollars. Find the mean for this data. So let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 data values in this sample. So we're going to find the mean. So x bar is going to be the sum of all of these values. So 50 plus 8 plus 24 plus 7. You get the idea. You can list them all out, or if you just want to say plus dot 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 all the way up to Bob Marley. And then we're going to divide by 13. And this is going to give us, I already did it, so if you add up everything in the numerator, you get 247. Divide that by 13. And then now we have 19.0. Why did I put a 0.0? Well, here's why. Because typically our rounding rule for the mean is that you round the sample mean to one more decimal place of accuracy than occurs in the raw data. So since my data had no decimal places, right, then I'm going to round my sample mean to 1. Now, it was just 0.0 anyways, so if I left it as 19, that would have been fine as well. Okay? Good. So that's the first measure of center, the mean. Now let's look at another one. This is called the median. All right, so the next measure of center that we're going to look at is the median. The median is the halfway point of a data set when it's arranged in numerical order. So from smallest to largest value. The median is denoted by capital M, capital D. That's the symbol that we use for it, typically. So if the number of observations, if your sample size is odd, Then the median is smack dab, it's exactly in the middle. Okay, you just got to figure out where the middle is. And then if the number of observations is even, then you're going to have two observations that split the middle. So the way you find the median is you're going to actually average or find the mean of those two middle observations in the ordered list. I'll show you exactly what I mean, okay? So first example, find the median for the royalties and estate earnings example above. So this example up here, where we found the average estate earnings, the mean, right? For these celebrities, now we're going to find the median. So we're going to first list all the data values in increasing order. I already highlighted 7 3 times. Those are the smallest values. Then next would be 8 twice. And then next would be 10 twice. I hope you're listing this as I'm saying it, because I'm just going to scroll back and relist. And then we have 19 just once, and then 20, and then 24. Next would be 35, then 42, and then 50. Okay, do you have your ordered list? All right, I'm going to go list it down here. So we had 7 3 times, 8 twice, 10 twice, then 19, 20, 24, 35, 42, and 50. And remember, we had 13 data values in this set or in our sample. So how can you figure out which one is supposed to be in the middle? So if you have an odd number of values, just add 1 and then divide by 2, and that'll tell you that the 7th data value in the ordered list is going to be your median. That's the middle point. So if you come through and start counting, so 1, 2, 3, 4, 5, 6, 7, right here, that entry is my median. Okay. Another way you could do it, you could just sit here and just cross off like 1 on each side, 1 on each side until you get there. But you know, if you have like 100 data values, I don't want you sitting there all day. So it's nice to have a way to figure out where the middle is without having to just cross off ones. And then I'll show you guys in a little bit how to do it on StatCrunch. Okay, let's look at one more example here. Find the median number of cloudy days per year for the top 10 cloudiest cities in the US. Oh, how sad. Okay, this is not in order. So let's list the data values in order. 209 is the smallest. Then there's 211 twice, yeah? What's next? 212, 213, and then we have 223, 227, excuse me, and then 229 and 240 twice. Okay. So they told me in the directions there's 10 cities, so that's an even number. So I already know the median is going to be the average of the 5th and 6th values in the set. So 1, 2, 3, 4, 5, and 6. I'm going to have to average these two guys. Again, you could do like cross off 1 on each side, 1 on each side, 1 on each side, 1 on each side. And then now you see, since there's an even number of values in this set, we don't have one that is smack dab in the middle. That's the median. So what we're going to do this time is average these out, find the mean. So you're going to take 213 plus 223 and divide by 2. It's always going to be divided by 2 because you'll only have 2 that split the middle. 436 over 2. So this median is 218. All right, very good. Last measure of center is the mode. And the mode is the value that occurs the most often in a data set. And the way I remember this is mode, most. You see that? 2 4-letter words, M-O-M-O. If no value occurs more than once, then we say the data set has no mode. Okay? So first example, find the mode for the royalties and estate earnings example above. So this example right here, can you see which data value occurs the most often? Want me to erase these little while you think about it? Which one do you see the most often? I see 7 here 3 times, and that's definitely the most. 8 was there twice, but that's not going to cut it. 10 is only twice. No, 7, 1, man. Okay. So the mode is 7. And since there's just one mode, we say that this is a unimodal data set. Remember, we talked about that word already when we were looking at distribution shapes, okay? Good. Let's look at another example. This is the duration in number of days of space shuttle voyages from 1992 to 1994. Okay, so is it in order? No, but we're just finding the mode. So let's see if we can identify who's popping up the most often. Here's an 8, 8, 8. Here's a 9, 9, 9. 14, that's just there once. And then I see 2 7s. So the most often, the values that appear the most often are both 8 and 9, right? They each appear 3 times. So this is an example of a bimodal data set. All right, very good. Now, one other idea I want to go over is that we've talked about distribution shapes and how data isn't always evenly distributed. It can be symmetric, but sometimes it can be skewed, left skewed, right skewed. We've looked at that. So what I want you to see is when the data is right skewed, remember that we have a bunch of values trailing off on the right, that means that the median is going to be less than the mean. It means you have more values here that are pulling or skewing the mean, the average, but really 50% of the data falls below the halfway point, which is here, which is, why it's good to look at both the mean and the median, especially when you don't have a symmetric data set. Notice in example B, the data is symmetric, so the mean and the median, they coincide. And then similarly, when your data is left skewed and you have like all these values trailing off to the left, they pull the mean. So the mean is going to be less than the median. So think whichever way the data is skewed, if it's skewed to the left, these values pull the mean away from the median, and that's why the mean is going to be smaller than the median when it's left skewed. And then here, when the data is right skewed, they're pulling the mean away from the median, so that's why the mean is larger than the median. Okay? Now we're going to look at larger data sets, and you're not going to have to compute this by hand. I'm going to show you right now how to do it in my stat lab with StatCrunch. Homework problem, I'm going to do number 4 from the chapter 3 homework. Each year, a magazine compiles a list of the 400 richest Americans. As of September 19th, 2012, 8 of the top 10 are as shown in the following table. Complete parts A through C below. So I know it's going to ask me for the mean, the median, and the mode in each of the parts. What I'm going to do is click this icon here and then say I want to open this data in StatCrunch. So give it a second to warm up. And then here it is. Notice all of our data is in this second column here under variable 2. So what you're going to do is click Stat, Summary Stats, and Columns, because our data is in a column. And it's in variable 2 column, so you got to select that so it knows where to pull from. And I'm going to select the mean, median, and mode. So on the right here is everything that StatCrunch is going to compute. So notice the mean is listed, a whole bunch of other stuff that I don't need. The median is here, and it doesn't have the mode. I know it's going to ask me for that because I previewed the problem. Okay, so I'm going to go through here and say I want the mean. I also want the median. So to select more than one, I'm just going to hold down Control and then click median. And then if you scroll all the way to the bottom, there's where the mode is. So hit Control and then click mode. So it's going to compute all three of these guys for me. And then I just select compute. Bam. So there it is. There's my mean, median, mode. I'm going to scoot this over, but notice, I don't make either window full size, so I can go between the two of them while I enter everything in. So find the mean for part A and pay attention here. It says type an integer or decimal rounded to 2 decimal places is needed. If you don't get that part right, it will mark it incorrect. So 2 decimal places for the mean, 32.0125. So notice 2 follows 1. I'm not going to round up then, so I'm going to enter 32.01 for the mean. Good job, yes. And then find the median. The median, I have it right here, 29.45. So I'll go ahead and enter that. Nice work, okay. And then find the mode. Select the correct choice below. The mode is, and here it gave me the mode of 31. There's an option to select no mode. If there wasn't a mode, then StatCrunch would say none under mode, but we do have one this time. It's 31. Excellent. So that's it. And you'll be able to use StatCrunch on the homework, on the quizzes, on the midterm. So I expect you to become familiar, not sit there doing stuff by hand. That is a waste of time. All right. Oh, I already did this one, so let's redo it. If you click similar question, it will just let you do the problem over if you want more practice or whatever. So the data set below shows the additional sleep in hours obtained by a sample of 10 patients given a certain medication. Complete parts A through C. So I'm noticing here it wants me to find N, the size of the sample. B is compute the sum of all of the data values, sum up each of these X sub i's, and then determine the sample mean. You could just easily do all this with StatCrunch again. So click this icon, open in StatCrunch, and it's all under variable 1 this time. So we're going to go stat, summary stats, columns. Which one? Variable 1. And I want N. I also want the sum of all of these values, which is right here. So hit Control, click it. And then the mean. I mean, I could find that myself, right? You just take the sum and divide by N, but hey, let's just let StatCrunch do all the work. So please compute these 3 for me, StatCrunch. Okay, so there's the results. N is 10. I mean, you could see that, right? 1, 2, 3, 4, 5, 2 rows. Yep, there's 10 values. Good. The sum of all of the values, 20.2. It didn't say how far to round, so just type in everything that's there, 20.2. Well done. Thank you so much. And then the sample mean, I mean, we could have done that very easily. 20.2 divided by 10, 2.02. That's it. I just want to show you something. Say they asked for the mode and you didn't realize they were going to want that and you already computed everything with StatCrunch. It's really not a big deal. You just click this again. I don't even think you need to. I think you can just come back here and then say you decided, oh my goodness, I need the mode and I didn't already get it. It's fine. Just pick this, go down here and say, oh, I totally forgot. Give me the mode too while we're at it. And then, oh, there's no mode. That's fine. So you can always, redo the stats. You don't have to start from scratch and do a new problem. Okay, you can recompute whatever you need to do. So that's it. Now let's move on to 3.2 measures of variation. And you might be saying, why do I need another way to describe my data set? I feel like measuring the center is fantastic. I got mean, median, and mode, gives me all sorts of information. Well, I want you to look at the following example. Look at these 2 different data sets. So say you had, I'll keep it simple, 0, 5, 10, 15, 20. That's data set number 1. And then the second one is 6, 8, 10, 12, 14. I want you to find the mean and median for each of them. Okay. So to find the mean for the first set, we'll just add everything up. 0 plus 5 plus 10, we're at 15, plus another 15, that's 30, plus 20 is 50. So 50 divided by 5 values, the mean is 10. The median, halfway point right here, is also 10. And then second data set, let's see here. Well, 6 plus 14, that's 20. And then 8 plus 12 is another 20, so we're at 40. Plus another 10, 50. Divided by 5, the mean is 10 here. And what's the median? It's 10 again. Both of the sets have no mode. So using our measures of center, if we only use the information that we looked at in the first section, both data sets have the same mean, the median, and mode. But would you say that they're equivalent? I mean, no way. Look, this first data set, all the values are more spread out, right? They differ by 5, and the values go all the way from 0 to 20. In the second data set, notice the values are closer together. They only differ by 2, and they don't span such a wide range of values. They only go from 6 to 14. So that's why it's important not only to identify where the center of your data is, but the spread of it. And the spread is basically what we mean when we talk about variation. Okay, so here we go. After determining the center of a data set, we can further describe it by quantifying or putting a number on that spread. So the first way that we can do that is by finding the range. So the range of a data set is denoted usually by capital R, and it's the difference between the highest and lowest values of the data set. So basically you just take the max minus the min, that gives you the range. So example here, the number of highway miles per gallon of the 10 worst performing vehicles is shown. Find the range of the data set. Oh my goodness, there's a car that gets only 12 miles per gallon. Wow. It says vehicle, maybe it's not a regular car. Okay, so there's the highest or the max. There's the lowest, that's the min. So the range, or R, is just going to be the difference between the two. 18 minus 12, which is 6. Good? All right, now we have two other measures, the variance and standard deviation of a sample data set. And that's going to be defined, those two will define through the following example. All right? So find the variance and standard deviation for the sample data given in the example above. So I'm going to walk you through the steps how we compute variance and standard deviation. The first thing you need to do is find the mean. You have to find the average. So take a minute, get your calculator out. Let's find the mean for the data set. So X bar is going to be 12 plus 15 plus 13 plus blah, 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 up until 18, divided by, they told me there were 10 vehicles in this set. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So if you add them all up, you should have 153. Divide by 10. So our sample mean is 15.3. Okay. Good. Excuse me. So now what we want to do is measure how far each data value is from that mean of 15.3. Okay. How much do they differ, or how spread out are they from the center of 15.3? So what we're going to do is take each data value and subtract the mean from it. So 12 minus 15.3, you're going to take each value minus the sample mean. That's what we're doing. So 12 minus 15.3 is going to give me negative 3.3. That makes sense that it's negative because 12 is lower than the sample mean, right? So it should be negative. And then keep going. 15 minus 15.3, negative 0.3. 13 minus 15.3, negative 2.3. 14 minus 15.3, negative 1.3. 15 again, we did that one. 16, positive 0.7. Now it's positive because 16 is larger, right? Or to the right of the mean. 17, 1.7. 16 again, 0.7. 1.7. And 18, 2.7. All right, so this column here expresses how much each data value deviates or is different from the mean, right? And it would make sense to get the spread of our data set that you would want to figure out, like, on average, how far is a value from the mean. But the problem is you can't average up this column right here. If you try to, if you take the total, why don't you guys do it? Pause the video really quick, total up this column and tell me what you get. Because you're like, oh, I want to see on average how far are my values from the mean. What happens? Did you do it? Okay. If you total up this column, you get 0. Okay. That makes sense because when we found the mean, we found the average of the data set. So it should be that some are smaller. That's why those values were negative. Some are larger. That's why they're positive. And if you just try to add them all up as is, the positives and the negatives will cancel each other out and you'll get 0. But that's not going to give us an accurate representation of the spread of the data set. So what we want to do is not have the positive and negative differences cancel each other out. And one way we can go about fixing that is by squaring all of them. Okay. So if you square negative 3.3, now it becomes 10.89. If you square negative 0.3, now it's positive 0.09. And I'm going to do this for the whole column. Okay. 5.29, 1.69, 0.09, 0.49, 2.89, 0.49, 2.89, and 7.29. All right. And now, obviously, since everything is positive in this column, if I add all these values up, I'm not going to get 0. So why don't you go take a second, add these all up, tell me what you get. Pause the video. All right, you should have 32.1, yes? Okay, so save this and let's just recap what happened. So here, we're interested in the average distance between a data value and the mean. But if we sum the x minus x bar column, that was this one, okay? The sum is 0. So to fix this, we square each result before computing the average. So now we sum the x minus x bar squared column right here, and we're going to divide the total by n minus 1. This is the sample variance denoted by s squared. So we had 10 values in our data set, didn't we? So n minus 1 is going to be 9 for us for this particular example. So the sample variance s squared is going to be this 32.1 divided by 9. And this is going to give us 3.6. This is my sample variance. All right. Good. Now, the rounding rule for the variance is you want to round the sample variance and standard deviation to one more decimal place of accuracy than occurs in the raw data. So notice here, I rounded to 1 decimal place at the end, and our data had no decimal places. For a hot second, I was keeping 2 just so that I would have the utmost accuracy, because you don't want to round until the very last step when it's time to report your final answer, okay, whenever possible. If you round too early, what happens is you're going to get a bunch of rounding error, because if you rounded this to 10.9, 0.1, 5.3, woo, you would not get 32.1, okay? So always wait to round your answer at the very last step. All right, good. Now, the square root of the variance, that is what is called the standard deviation, denoted by S. So our standard deviation is going to be the square root of the variance, which we have right here, 3.6. And I'll round that to 1.9. That's my standard deviation. And that basically tells you, on average, how spread out or how far your data values are from the mean. The reason we take the square root here to get the standard deviation is essentially to undo the fact that we squared all of those differences before we added them together, okay? Now, it's going to be your job to understand and interpret what the variance and standard deviation tell you about a data set. You will never have to compute it by hand like this ever again, okay? So I just wanted to demonstrate what they represent by walking you through an example, but please don't waste seconds of your life that you'll never get back sitting there doing calculations that we have technology to do for us, okay? Computers don't think and analyze data sets. That's what we're doing. That's why we're studying statistics. Let them just crunch out the values and then you do the analysis, okay? And another rule to keep in mind is that almost all observations in any data set lie within 3 standard deviations to either side of the mean. So once you find your mean and your standard deviation, if you add the standard deviation 3 times to the mean and subtract it 3 times from the mean, almost all of your data set is going to be within that range, okay? So now I'm going to show you an example with StatCrunch, how we're going to find the standard deviation and all that good stuff. Don't do it by hand. I mean, unless you're really inclined to, but there really is no point, okay? There's no point. Into the homework, I want to start with number 6. Consider the data set in the accompanying table. Complete parts A through C below. So the data set's here, and I'm going to go ahead, click to copy the table. Let's open it in StatCrunch. And there it all is. Okay, so let's scoot this over. I'm done looking at it. Part A, it says use the defining formula to obtain the sample standard deviation. Okay, so ignore them. Don't use the formula, you guys. There's really no point. We're going to use StatCrunch. So we need S, the sample standard deviation. Again, you're going to click Stat, go down to Summary Stats, Columns, Variable 1, and the standard deviation's already here along with a bunch of other good stuff. So let's just say compute. Beautiful. All right, it tells us here, round to 3 decimal places as needed. So here's my standard deviation, 2.7386. So since there's a 6 following the 8, I got to round it up to a 9. So this is going to be 2.739. Bam, fantastic, thank you. Replace the 9 in the data set by 99. And again, use the defining formula. No, we're going to use StatCrunch to compute the sample standard deviation. So what it wants us to do is come back here and replace the 9 with a 99 instead. Wowza. Okay, so the data was 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we jump from 8 to 99. What do you think that's going to do to the standard deviation? Remember, it's measuring spread, right? So Stat, Summary Stats, and we're going to go to Columns again, Variable 1, and here it already is going to compute all this stuff, so let's go for it. And look now, the standard deviation, 31.583. Wow. And after the 3 is a 2, so I'm not going to round that up. 31.583. Excellent. Thank you so much. Now compare your answers in parts A and B. The lack of what property of the standard deviation accounts for its extreme sensitivity to the change of 9 to 99? Well, notice here the standard deviation is a lot greater in part B. And all we did was change one little data value. And the problem is that when we're computing all the differences from the data values to the mean, there's no way for us to rule out if there's just an extreme value that's making it look like the data is more spread, right, than it really is. So we can answer this now. The standard deviation in part B, well, it's greater than the standard deviation in part A. And the standard deviation isn't, let's go through the options. It's not resistant to outliers. We'll talk more about what an outlier is, but that's an extreme value that does not fit within the span of most of the data. The other options just don't make sense. The standard deviation isn't the appropriate measure if the data set changes. That doesn't really make any sense. It isn't the preferred measure of variation. It really depends. It's not the appropriate measure for small data sets. No, that doesn't matter. So it's not resistant to outliers. Okay, check your answer. We're so good. Moving on. Okay, I just did this problem, so let's redo it. Here we go. A study is published with information about the ages of people in a particular region. A sample of 5 residents from the region have the following ages in years. So determine the range. You could do that by hand, but let's practice using StatCrunch. So stat, summary stats, columns, variable 1. Is it going to give me the range already? Just check through. Yep, there's the range. Okay, compute. So the range is 73. Type that in here. Oh, let me scoot this over. So 73. Fantastic. Thank you so much. Find the sample standard deviation using the formula. Don't use the formula, just use StatCrunch. And it says the standard deviation is 30.138. Oh, this time we're only rounding to 1 decimal place. You guys, they're gonna change their mind about the number of decimal places. So just pay attention. So just 1 decimal place, that's gonna be 30.1. Excuse me, 30.1. Excellent, thank you. Now they want you to practice doing the standard deviation with a different formula by hand. Who cares? I mean, if you really are desperate to experience the formula, go for it. But I will never test you on it, nor is it going to be essential, when you're becoming a statistician. Okay, compare your work in parts B and C. Well, they're the same, and that's all you have to say here. They are the same. So there's 2 different formulas when you're computing standard deviation by hand, okay? This second one sometimes is meant to be a little bit easier when you're doing it by hand. That's all fine and dandy, but we're never going to do it by hand. So just enter what you have from StatCrunch and move on. And then let's do another one. So the article, Material Culture as Memory, Combs and Cremations in Early Medieval Britain. Okay. Discusses the frequency of cremation burials. So data for the sample of 15 of the 17 sites can be found below. Obtain the sample standard deviation. Okay, let's open this in StatCrunch. Load it up, StatCrunch. Okay, like this for sure, who would want to do it by hand, right? That would be such a nightmare. So stat, calculators, no. Summary stats, yes. Columns, compute. Okay, we're rounding to 1 decimal place. So standard deviation, it's 619.95, but the 5 is going to round the 9 up, and then that's going to round the next 9. So it should be 620.0. Well done. Yes. Do you think in this case, the sample standard deviation provides a good measure of variation? Well, let's see. In this case, the sample standard deviation does not provide a good measure. For sample sizes smaller than 20 that are roughly symmetric, the range provides a better measure of variation. We've never talked about sample size being an issue, so that's not sounding appealing. In this case, the sample standard deviation does not provide a good measure of variation because it is not resistant to outliers. Therefore, its value is strongly affected by a few extreme observations. Does that apply here? Do we have some extreme observations? 265, 258, 40, 86, and then look at this 2,484. That's really not fitting in with the rest of the data. That's what we're going to call an outlier. And that seems to apply. So B, I'm going to think about that one. C, in this case, the sample standard deviation provides a good measure of variation because the sample size is greater than 10 and is roughly symmetric. Is it roughly symmetric? I don't know about that. If you want, remember when we graphed data before? Why don't we just put a little histogram together? Yeah, StatCrunch can do that for you too. Compute. Does this data look symmetric? No, right? It's definitely skewed to the right. You could do a different kind of graph too if you want. Play around with it. You want to do a dot plot? Having too much fun. Ooh, I like the dot plot better because you can see each value. And yeah, again, it's definitely skewed to the right. We've got this outlier here, the 2,484, and then the other values are all clustered over here. So this sample is not roughly symmetric, so it can't be C. D says, in this case, the sample standard deviation provides a good measure of variation because it is preferable to the range and interquartile range for standard data sets. No, so I'm leaning towards B. In this case, the sample standard deviation does not provide a good measure of variation because it's not resistant to outliers. And that 2,484 is definitely making the standard deviations larger, right? And not accurately express the spread of the data. The data is not all that spread out, you know. Let's check. Look at us. We're so good. Okay. So that's it for standard deviation. All right, now let's look at section 3.3, Chebyshev's rule and the empirical rule. We're actually going to look at the empirical rule first. So the empirical rule you can use when your data is normally distributed. What do we mean by that? If your data is bell-shaped, okay, or normal. Then the following statements hold true. Approximately 68% of the data will fall within one standard deviation of the mean. Approximately 95% of the data will fall within 2 standard deviations of the mean. And approximately 99.7% of the data will fall within 3 standard deviations of the mean. Remember, we looked at the 3 standard deviation rule earlier that said almost all the data, almost all, will fall within 3 standard deviations of the mean. If our data is normally distributed, that equates to about 99.7%. So I'm going to zoom out actually so you can see a little bit better what's going on here. So here's our sample mean X bar, and we can use the empirical rule when our data is normally distributed or bell-shaped. So what that means is it's approximately symmetric, unimodal, okay? And the standard deviation S, if I add that to the mean, subtract that from the mean, that means that, or that equates to 68% of the data lies in here. So 68% is right here within 1 standard deviation. If I extend that to 2 standard deviations, okay, now we have 95% of the data within that range of values. And then if we go as far as 3 standard deviations away from the mean, we have 99.7% of the observations lying within there. So that means there's just 0.3% on either side left. And then that you would cut in half, right? So half of 0.3% on either side. In order to use the empirical rule, though, you do need to know that the data is normally distributed. So keep an eye out for that when you're working on a problem, okay? So let's look at an example. You got to just memorize these numbers. You got them? 68, 95, 99.7. Put them on your note card. That way you're ready when the midterm comes. Okay. Let's look at some examples. These are fun, don't worry. Don't fret. So, first example, the scores on an achievement test are normally distributed. So that tells me, yep, you can use the empirical rule with a mean of 1,000 and standard deviation of 120. Okay, so that means X bar is 1,000. Standard deviation, that's S, that's 120. So the first part is asking me approximately 68% of the scores will fall between. So what I'm going to do, I'm not going to draw the bell curve part. I don't need that. I know from the empirical rule that 68% of the data values lie within one standard deviation of the mean. So if the mean is over here, here's the mean at 1,000, within one standard deviation on each side, so x bar plus 1s or x bar minus 1s, I'll have 68% of the data values or the scores. So can you figure out what they are? So 1,000 plus 120, that would be 1,120. And then 1,000 minus 120, that would be 880. So approximately 68% of the scores will fall between 880 and 1120. That's literally all there is to it. Don't worry, they won't ask you anything other than 68, 95, or 99.7. They won't say like, what do 65% of the scores fall between? You would need some other tools that we haven't learned yet. So when you're using the empirical rule, you're only going to be asked percentages that correspond to the values that we have, okay? Next part asks us 95% of the scores will fall between. So we know from the empirical rule that equates to 2 standard deviations, 2 S's. So let's go ahead and add the standard deviation and subtract it again on either side. So 2 standard deviations, if I take x bar plus 2s and x bar minus 2s, where are we? So 1120 plus another 120, that's going to be 1240. And then 880 minus 120 is going to give us 760. So 95% of the scores will fall between 760 and 1240. Lastly, it asks for 99.7% of the scores. What will they fall between? Well, this equates to 3 standard deviations. So let's go ahead, add another 120 and subtract another 120. So 1240 plus 120, that's going to be 1360. And then 760 minus 120 is 640. So this would be between 640 and 1360. And that's all there is to it, okay? Again, they won't ask you 99.5% of the scores. That doesn't match up with what we know from the empirical rule. All right, let's look at another example. The average U.S. yearly per capita consumption of citrus fruit is 26.8 pounds. You know, I don't know if I buy that. Really? I'm not eating 26.8 pounds of citrus fruit a year, so I'm falling below that mean. Anyways, suppose the distribution of consumption is bell-shaped, is it now, with a standard deviation of 4.2 pounds. What percentage of Americans would you expect to consume less than 18.4 pounds per year? Okay, don't get overwhelmed. Okay, don't zone out. You can do this. So average consumption of citrus fruit is 26.8. That's my X bar. And then they told me it's bell-shaped. Here's the standard deviation. So S is 4.2. And they want to know what percentage of Americans would you expect to consume less than 18.4 pounds per year? So let's always just draw like a rough distribution. X bar is going to go right in the middle, 26.8. And you don't have to draw the bell curve. If you want to, you can, whatever. They want to know what percentage of Americans would you expect to consume less than 18.4 pounds per year. So say here's 18.4. They want to know how much or what percentage of the data is below there. Okay. So since this is bell-shaped or approximately normal, we can use our empirical rule. And to answer the question, I want to know how many standard deviations are between 18.4 and 26.8. They told me the standard deviation is 4.2. Okay. So notice if I subtract these two data values, 26.8 minus 18.4, what do I get? I get 8.4. And 8.4 divided by 4.2 is 2. So there's 2 standard deviations sitting in here. And you could just keep subtracting 4.2 if you wanted. So 26.8 minus 4.2, what would that be? That would be 20, hold on, I didn't do this earlier. So now we're doing it together, which is good. 26.8 minus 4.2, this is 22.6. And then you could subtract 18.4 again. Subtract 4.2 and you get 18.4. So there's 2 standard deviations sitting here. So what do we know from the empirical rule about 2 standard deviations? Well, it means 95% of the data is in here. And so we have 5% split amongst the remaining values. So there's going to be 2.5% in each of these tails here. So now they're asking, what percentage of Americans would you expect to consume less than 18.4 pounds per year? Well, I would expect 2.5%. Okay. And they're going to always ask it so that it works out to be 1, 2, or 3 standard deviations. Okay. Let's look at another example similar to this one. The average national SAT score is 1019. If we assume a bell-shaped distribution, okay, so we can use the empirical rule, and a standard deviation equal to 110, what percentage of scores would you expect to fall above 1129? So here's the average. X bar is 1019. S is 110. So let me draw my distribution. Here's the average, 1019. And they want us to figure out how or what percent of the scores fall above 1129. So how much is in here? So how many standard deviations are between 1019 and 1129? Okay, well, the standard deviation is 110, and these are exactly 110 apart. So that's just 1 standard deviation. And what do we know from the empirical rule? We know that 68% of the data lies within 1 standard deviation of the mean. Underneath the curve is 100% of the data. This is supposed to be symmetric, so excuse the ugliness, okay? Okay. So 68% falls there. 100% is everything underneath the curve. 100 minus 68 is 32%. That's split between this tail and this tail. So cut it in half. That means there's 16% left over that is not within 1 standard deviation of the mean. So if they're asking what percentage of the scores fall above 1129, bam, you have it right there, 16%. Okay, good. Now you might be thinking, well, what do we do when the data is not normally distributed? Well, we have Chebyshev's theorem to give us another way to approximate how much data is within a certain number of standard deviations. So Chebyshev's theorem tells us the proportion of values from a data set that will fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k is greater than 1. This gives us the proportion. So it's going to give you a decimal, right, or a fraction between 0 and 1. If you want to equate it to a percent, then you would just multiply by 100. And note, this is the important thing, a distribution does not have to be normal to apply Chebyshev's theorem. Okay? If it is normal, Chebyshev's theorem is going to underestimate, right? It gives you a conservative estimate for how much data is within a certain number of standard deviations. Like if you use k equals 2, that means 1 minus 1 over 2 squared, or 1 minus 1/4 of the data is within 2 standard deviations of the mean. 1 minus 1/4, that's 3/4, which is 75%. And from the empirical rule, we had that within 2 standard deviations, there was 95% of the data. So Chebyshev's is always going to give you an underestimate compared to the empirical rule because we don't know that the data is normally distributed. It may not be, so you can't assume that you have as much lying close to the mean. It might be skewed. So that's why Chebyshev's theorem or rule gives you like a conservative estimate in case you have some like really funkily distributed data. Yes. Okay. So let's just look at how to apply it. Example, a survey of car rental agencies shows that the average cost of a car rental is 32 cents per mile. So let's write that down. That's my X bar. And the standard deviation is 3 cents. So S is 0.03. Using Chebyshev's theorem, find the range in which at least 75% of the data will fall. So 75% of the data, I want to know how many standard deviations, or what is K equal to, for 75% of the data. Well, we literally just looked at the fact that K equals 2 equates to 75% of the data. What if we hadn't just done that though? What would you do? Not sit and cry. No, you would go 75%, that's 0.75. And Chebyshev's rule tells me 1 minus 1 over K squared of the data falls within K standard deviations. So if I were to subtract 1, boop, boop, then I have negative 0.25 equals negative 1 over K squared. The negatives cancel out. 0.25, you guys, is 1/4, right? So 1/4 equals 1 over K squared. You can cross multiply or just take the reciprocal of both sides of the equation and we get K squared equals 4. And so K is going to equal, you don't need to put the plus or minus, it's just going to be 2 standard deviations. Okay. All right, so now we want to figure out what the range is, or what value is 2 standard deviations above the mean and what value is 2 standard deviations below the mean. So on my range, the upper limit is going to be the mean, which was 0.32, plus 2 standard deviations, so 2 times 0.03, which is 0.06. So 0.32 plus 0.06, that's 0.38. And then the lower limit, or the lower end of the range, would be 0.32 minus 2 standard deviations. 0.32 minus 0.06 is 0.26. So here's the range. At least 75% of the data is going to fall between 0.26 and 0.38. You could just write it like that. If you are asked to give an interval though, I don't know how much algebra you guys have had. Interval notation, you list the values in increasing order. So 0.26 would come first. You put a comma, 0.38 after, and then parentheses. And that's interval notation. All right, if they ask for an interval. Good? Okay, let's look at another example. A survey of local companies found the mean amount of travel allowance to be 25 cents per mile. So that's the mean. Let's list that now. So X bar is 0.25 with a standard deviation of 0.02. Okay. Using Chebyshev's theorem, find the minimum percentage of data values that lie between 0.20 and 0.30. All right, so here's what's going on. X bar, the mean, is here at 0.25, and they want to know what percentage of values fall between 0.20 and 0.30. So what percent is in here? Okay, well, the first thing I need to know is how many standard deviations is each of these values away from the mean. So remember, we've done this before. I'm just going to subtract these two values and then divide by the standard deviation to figure out like how many S's are sitting in there, right? So 0.25 minus 0.20 divided by 0.02. I take the difference, which is 0.05, divide by 0.02, and I get 2.5. So K, or the number of standard deviations that 0.20 is from 0.25, it's 2.5 standard deviations below the mean, okay? And then we could check 0.30. I can already tell though it's going to be the same, right? These values are evenly spaced from the mean, but we should double check. So 0.30 minus 0.20, and then divide by 0.02, again 0.05 over 0.02, you get 2.5, which is our K. So now we just have to figure out, using Chebyshev's rule, if K is 2.5, what percentage does that equate to? How much of the data is between 0.2 and 0.3? So you're just going to say, all right, 1 minus 1 over K squared is going to be 1 minus 1 over 2.5 squared. And you can go ahead and get your calculator. 1 minus 1 divided by 2.5 squared, and I get 0.84. And the problem asked for a percentage, so that means a minimum of 84% of the data lies between these two values, 0.20 and 0.30. You see how that works? Okay, it could be more. It could be more. I just don't have the distribution and I can't assume that it's normal. So this is playing it safe, guys. Playing it safe. All right, one more. A barber takes an average of 14 minutes to give a haircut. What a stud. Okay, so X bar is 14. Who timed him? With a standard deviation of 3 minutes. If nothing is known about the distribution, what would be the interval in which at least 8/9 of the data will fall? So again, I want to know 8/9 of the data is equivalent to how many standard deviations from the mean. So Chebyshev's rule tells us 1 minus 1 over K squared. That fraction, or that proportion of the data, lies within K standard deviations of the mean. So I'm going to set that equal to 8/9. Now let's go ahead, subtract 1. I mean, you might be able to figure out what K is just by looking at it. If so, good for you. Some people have like really stellar number sense. If not, we can always solve, so don't freak out. Negative 1 over K squared equals 8/9 minus 1. That's 8/9 minus 9/9, right? So that's negative 1/9. Again, the negatives cancel out. You can cross multiply or just take the reciprocal, flip both sides of the equation. So K squared equals 9. And then that means K is equal to 3. Okay. So the interval in which 8/9 of the data will fall corresponds to 3 standard deviations above and below the mean. So to get the upper bound, I'm going to take 14 and add 3 standard deviations. So 3 times 3. So that's 14 plus 9, so 23. And then to get the lower bound, I'm going to take 14 and subtract 3 standard deviations. So 14 minus 9, that's 5. And then you see how this time the problem asked for an interval. Well, we are ready. We know how to write our answers in interval notation. From 5 to 23, you always have to list them in increasing order. Put a comma between, and you're done. Bam. Okay, so that concludes the lesson. After this, we're going to move on to 5-number summary and box plots, and then descriptive measures for populations, use of samples. But that's in the next video. So take your time with the homework. Use StatCrunch. Don't sit there doing standard deviation by hand unless you just really are inclined and need to prove it to yourself. Have a great one, you guys. Don't forget to give the video a thumbs up, subscribe if you haven't already, and share it with all your friends and family. They'll love it too, I think.